So here's one for you to do everything on. Right? So if you're not sitting next to somebody, get next to somebody, all right? And work on this together. Let's spend a little bit of time on this one. And here, let me just give you your tasks here in pink, all right? In step 1 here, I want you to write the half reactions. In step 2, I want you to calculate what E naught of the cell is. And then in step 3, I want you to calculate what the delta G will be. That's in kilojoules. And then in step 4, I want you to go ahead and write this cell as a shorthand. Meaning where we have the 2 compartments, and we show what's happening in those 2 compartments. All right, it's a process. Go ahead and get started. Work with each other. Ask questions. Yes, no, maybe so. Yeah. All right, let's just run through everything real quick. Make sure that you did it all correctly. So, step 1. Now, first of all, you're not told whether this is spontaneous or not. All right? And here's a diagram of the cell. And I told you that our convention is typically the anode is on the left and the cathode's on the right, meaning that oxidation's happening on the left and reduction's happening on the right. But the textbook doesn't always follow that convention, and I think this one is backwards. That's okay, because you're not looking at the picture, you're looking at the reaction, right? Let's take a look. And we're already looking at the net ionic equation, and you're told that it's an excess sodium sulfate. So the net ionic equation tells us that manganese solid is going to manganese 2+. So is that oxidation or reduction?
Oxidation.
That's oxidation. So let's write the oxidation half reaction. That's going to be manganese solid is being oxidized to form manganese 2+ plus 2 electrons. Oh, this is an aqueous solution. All right, which means that the opposite must be happening to the other material. There's only one other choice here. That's the zinc. The zinc 2+ is being reduced. So the reduction half reaction is going to be zinc 2+ plus 2 electrons goes to zinc solid. Okay, that's good. Now we need to calculate E naught of the cell. So we go to our table and we have to look at, remember, E naught is a reduction potential. It's not an oxidation potential. This part of this chapter is probably the most confusing to everyone, just because you have to figure out, what's happening at the cathode and what's happening at the anode, and when do I flip it and when do I not flip it, and all that stuff, okay? And the reason, it's not my fault, all right? I'm just trying to make it easy on you. The reason it's difficult is because we have designated the standard hydrogen electrode, She, to be our 0, okay? All you're doing is looking at the difference between one reduction potential and the other one. So let's find these on our table. Now this table is already kind of drawn on. So I think I have another table down here. Here, let's just use this one. So we're looking at manganese, which is where? Where is manganese here? Here it is. Now that's manganese being reduced, okay? When manganese gets reduced, it has a reduction potential of negative 1.185. We're also looking at zinc, which we've looked at before. Zinc is up here. When zinc is reduced, it has a reduction potential of minus 0.672. So when we put these in competition, the one that will get reduced will be the one with the highest reduction potential, which means this is going to get reduced, which means this gets oxidized. So we take whatever that reduction potential is and we reverse it, because the reaction is going backwards. It's going in reverse. So that's all we're doing. So let's put that in. Now, we know that reduction happens at the cathode and oxidation happens at the anode. Right? That just makes it convenient when we write this as an equation. But you can also just think about what you're doing. You can just look at the table and figure out what you're doing. So let's put these numbers in now. So the reduction was the zinc, and that was minus 762. And we're going to subtract from that the reduction potential of now what's being oxidized, right? Which was the manganese. That was minus 1.185. So the E naught of the cell is going to be whatever that is. What is it? 423 plus 0.423 volts. All right, now we need to calculate what delta G is for this standard reaction. Now I emphasize standard because this is all E naught, right? E naught, this is standard conditions. Let's do a review. What are our standard conditions?
1 ATM.
What?
1 ATM.
118?
1 ATM.
Oh, 1 ATM, sorry. Yeah, 1 atmosphere, it's really 1 bar. Okay, but that's about the same as 1 atmosphere. What about temperature?
25 degrees.
25 degrees. And what else? And 1 molar of everything. Those are our standard conditions. And that's all we're dealing with, okay? Maybe at the end of today, I'll tell you how deep this can actually go when we're not under standard conditions. That's something called the Nernst equation. Okay, so under standard conditions, that's what E naught of the cell is going to be. We need to figure out how many moles of electrons are being transferred here. How many are transferred? There's 2. You can see that in the oxidation and reduction half reactions. We didn't have to do any fancy business to balance them because it turns out on this one, they're both 2 electrons. So we don't need to balance those. If we did balance them, that's fine. That just tells us how many moles of electrons are being transferred. But if we had to change the coefficients on the half reactions to balance the electrons, that doesn't alter the voltage potential. The voltage potential is based on the reduction potentials regardless of how many electrons there are. Okay? That's another thing that students don't quite always understand. All right, so we have 2 moles of electrons transferred, so delta G is going to be equal to negative 2 times Faraday's constant, 9.56 times 10 to the 4th coulombs, multiplied by the cell potential, which is plus 0 point.
Is Faraday not 6'5"?
Is it 6'5"?
Oh, it is 6'5".
Sorry.
You did that last time.
You know, of all the things that I keep in this little brain of mine, Faraday's constant is one that I just can never remember. It's 6'5"? Okay. You'll have that on your formula sheet. 423 volts. That answer, whatever it is, that's going to be in joules. Okay, because joules have the units of Coulomb volts. So if you then change that into kilojoules, I think the answer I said was what? 18? No, 81? What was it?
Yeah, I think it was.
I think I said 81. Here it is. Minus 81.6 kilojoules per mole. Now, you might say per mole of what, right? Per mole of that reaction. Per mole of that reaction when 2 moles of electrons are being transferred. Is this equation, is it spontaneous in the direction that it's written in?
Yes.
It should be, because when we calculated all this, we get a positive value for E, and we get a negative value for delta G, so it should be spontaneous. Now, the shorthand, right, when we do the shorthand, that's just looking at what happens at the anode on the left-hand side and what's happening at the cathode on the right-hand side. And so we start with the actual electrodes. So solids are on the opposite sides, and then whatever those things are in aqueous solution. So in this case, the anode, that's where oxidation is occurring. The oxidation is the manganese. So this would be, we start with manganese solid, and then that gets turned into manganese 2+. So that's on the anode side, and then on the cathode side, we start with zinc 2+ in aqueous solution, and we end up with the zinc cathode at the end. So that's how you would do the shorthand. Because I've been calling these electrochemical cells that we're working with, and they are electrochemical cells, but especially in the textbook, they're a little more particular about the words that we use, okay? Because as you're reading, you may find that these are also called voltaic cells. Sometimes they're also called galvanic cells. Those words are interchangeable. Actually, they're named after the people who invented these. I even have their names written down here. Should I tell you who they are? This is Alessandro Volta. I have to look at how it's spelled. Not that I would give you an exam question on this. Or Luigi Galvani. And in fact, the particular cell that we've been looking at with zinc and copper, that has a specific name for it. That's called a Daniell cell. And again, this is just more for your information. But if you're reading along in the chapter, you'll see that these are interchangeably referred to as galvanic cells, voltaic cells, or electrochemical cells. And I certainly use those terms interchangeably as well. But you should get to know that all three of them are really describing what we were talking about the last lecture, where we're taking a redox reaction and we're dividing it into two separate cells such that we can extract some electrochemical work out of the redox reaction. Now, more in particular, if you really wanted to see what was different about these terms, a voltaic cell is just as written here, where the reaction is spontaneous. So when we set up the cell and you get a positive value for the standard cell potential, that would be what we would call a galvanic cell or a voltaic cell. It's basically running in spontaneous direction, okay, which means that the E of the cell is going to be a positive value, and delta G, if we were to plug that into, this delta G is equal to minus NF E of the cell, that would be a negative number because we associate negative delta G with spontaneity. And if it's non-spontaneous, everything's in reverse. So technically then, an electrochemical cell is where we get it to run in reverse, but to do that we need to supply some energy. So we need to apply some kind of power supply here, and that's what we have here. So for an electrolytic cell, for example, we need to supply that energy. So we have a power supply, and it basically runs it in reverse. And of course, if we're running something in reverse, that means that the reaction that's in reverse, it has a positive delta G and a negative value for the voltage potential of the cell. So I just wanted to highlight that for you. So when you see these, you can think of them as being interchangeable. Now, I also want to mention that we've been working with standard cell potentials. Which is E with the little not sign. Okay? And I want to remind you that the standard is at 25 degrees Celsius or 298 Kelvin and atmospheric pressure, so 1 atmosphere, but really it's 1 bar, which is very close to 1 atmosphere. But most importantly, everything's at 1 molar concentration. Okay? Now soon, either today's lecture or on Monday, we're going to be departing from standard conditions. And when we depart from standard conditions, we can still calculate what the voltage potential of the cell will be, but it's no longer going to be the standard potential. There's a relationship between the standard potential and what the actual potential is. And you may recall back in the thermodynamics chapter, there was a difference between delta G and delta G naught. Right? If you don't remember that, we'll talk about that in a little bit. Right? But it's very parallel here. Okay? So, just wanted to remind you, keep your eyes focused on the overall forest as we get back down into the trees again. So, I left you off with this slide here, and a few more things. Actually, since we're on here, let me squeeze these guys down now. We don't need their names anymore. So I'll remind you of a few more things that were on this slide, because here we were just calculating what the standard cell potential is, when in this case we have copper and aluminum. All right. We calculated what the standard voltage potential is, 1.508. But we also then balanced the redox equation so that we had the right number of electrons in this reaction. So we knew that for 1 mole of this reaction, we actually were transferring 6 electrons. And that didn't have an effect on the voltage potential. Remember, the potential is the potential. It stays the potential regardless of what the flow is over it. The flow is the moles of electrons going over that potential. And for 1 mole of this reaction, we have 6 moles of electrons going over that potential, which means that the energy we can get out of that standard cell, we can calculate using this equation, where N is the number of moles, F is the Faraday constant, and E naught of the cell. Okay? All right, so here's your table again. I don't know if this is the exact same one or not. There's 3 challenges on here. The first 2 are straightforward, and the last one is difficult. And all you got to do is answer which ones are spontaneous and which ones aren't. Now, you do need to make sure that you use the exact reduction or oxidation half reaction when you're going to the table. Because you'll see that zinc, for example, appears in other places on this table when it's in different forms or in different compounds. So you do need to make sure you understand what the half reactions are before you go to this table. Now, I see you all calculating stuff. You're probably writing out half reactions and writing out voltage potentials or reduction potentials. But just take a look at these. Stop what you're doing real quick. All right? Take a look. All right? I color-coded these for you. So the top one's in blue. No, the top one, yeah, the top one's in blue. You've got copper solid and chlorine gas. You got to just identify what's being oxidized and what's being reduced, first of all. Right? That's an easy, relatively easy challenge now. We've been doing that a lot. Copper solid is going to copper 2+. So is copper being oxidized or reduced? Oxidized, right? It's losing electrons. So take a look at the copper. All right? Copper being oxidized, copper solid being oxidized. There it is in the lower right. And we're challenging it with chlorine gas. That was a neutral going to chloride ions. So is that being, obviously that's being reduced. So we've got chlorine gas being reduced in the upper left at the expense of copper solid being oxidized in the lower right. Boom, it's spontaneous using the shortcut. Now you can go ahead and write out the half reactions and whatnot, and same skill with this one. All right, silver plus is going to silver solid, so that's being reduced. So silver plus is being reduced, and there it is in the upper left. And we've got zinc solid going to zinc 2+, that's being oxidized. So we have zinc solid being oxidized. There it is in the lower right. Boom. Spontaneous. Upper left, lower right. I should do it this way. Upper left, lower right. Okay? So this one's a yes. This one's a yes. Reaction. What's being oxidized and what's being reduced? And remember, the oxygens unless you've got O2 gas. O2 gas is neutral, because that's how you find it in nature. Oxygen, in almost every other compound except hydrogen peroxide, is going to have a 2 minus charge. So that means the zinc here is what? The zinc is 2 plus. The zinc here is 0. The hydrogen is neutral, and here the hydrogen is 1 plus. So we did something very similar to this already, right? The zinc 2 plus, this is being reduced, and the hydrogen is being oxidized. But now we got to find these in the table. And this is where you have to be really, really careful. You've got to define what the half reactions are and then find them in the table. It's not going to be solid zinc. Zinc doesn't come in as solid zinc. Now you take a look, where else do you see zinc on the table? Well, here it is. Here's zinc oxide plus H2O becomes becomes reduced to form zinc solid and 2 hydroxide ions. So let's write that one down. Zinc oxide solid plus H2O liquid gets reduced with 2 electrons to give us zinc solid and 2 hydroxide ions in aqueous solution. Okay. Now, this is a hydroxide in aqueous solution. What do you know about hydroxide ions in aqueous solution? What does that do to the solution? Say it louder. It makes it basic, right? pH. What's another word for basic? Alkaline. Okay? So this is in an alkaline solution. And in writing this reaction out, we recognize that it's in a basic environment or an alkaline environment. So these are the kinds of reactions that we have in alkaline batteries, for example. Now to find the oxidation reaction, right, that's going to be hydrogen is being oxidized into H plus that we have in H2O. We need to find that on the table as well, and it's not straightforward because hydrogen being oxidized or reduced is present several places on this table. You need to find the one where it's in a basic environment, where you have hydroxide ions. And as you look through the table, you find that the one that we're interested in is right here. This has the reduction of hydrogen into hydrogen gas in a basic environment, 2OH minus. That's the one that we need to use. Now, of course, it's being oxidized in this case, so we need to write it in reverse. That's going to be 2OH minus aqueous plus H2 gas goes to 2H2O liquid plus 2 electrons. Okay, and if we were to add these up now, we'll find that they add up to the equation that we want to characterize up there. 2OH cancels with 2OH, 2 electrons cancels with 2 electrons. What else cancels? Anything? We've got H2O here. We've got one H2O here cancels with one of those here. So that then, you can see, you can write that down. That's going to give us zinc oxide solid plus H2 gas goes to, I'll put it in the right order here, zinc solid plus H2O liquid. Okay? So that just shows you grabbing the right two half reactions to describe this overall redox equation. Now, the ultimate question is, and on this slide, is as written, which one of these reactions is spontaneous and which one is non-spontaneous. In this case, we're evaluating these two half reactions, and this is a skill that you should know how to do, okay? But the way it's written, the way it's presented to us, all right, this is the one, zinc oxide is being reduced, so this one here is being reduced, and this one here is being oxidized. And that's not what you would expect for the spontaneous reaction, right? Because The one that gets reduced is the one with the higher reduction potential. You see that? You can also do this with the upper left, lower right idea. In the, right here, all right, in the middle, okay? In this case, what's being reduced is the zinc plus is being reduced. And what's being oxidized is this. This is being oxidized. And that's reversed to what we were expecting. For it to be spontaneous, we want the thing that's being reduced in the upper left and the thing that's being oxidized in the lower right. And this is the opposite of that. So you could do it that way if you want to use that shortcut rule, or you just look at the reduction potentials. The one that gets reduced is the one that has the higher reduction potential. So this reaction as written would not be spontaneous. Okay? But that was shrouded in a more complex set of half reactions that you needed to go and find in this table. So again, that's in an alkaline environment. Now, a lot of the examples in this chapter, they like looking at batteries. All right, wet cells and dry cells. I'll just show you this in the context of one of these battery examples. But here's an alkaline battery, all right, that you're used to using, I'm sure, every day, okay? And here's the reactions, right? Here's that reaction that we were just looking at with the zinc oxide. You can look in the figure to see how this is all set up. Now, which one here is being reduced? We have two reduction half reactions written here. Of these two, which one's going to get reduced? Number one. So this one is going to be reduced, and this one then is going to be oxidized. So we can write all that out. So the reduced reaction, number 2, that's going to be 2 manganese oxide solid plus H2O liquid plus 2 electrons gets reduced to another manganese oxide. So what's the difference between the manganese oxide on the left-hand side and the manganese oxide on the right-hand side? What's the difference? I can't call it manganese oxide, can I? I have to define what's the difference between them. What's the charge state on the manganese in MnO2? It's 4+, that's right. What's the charge state of manganese in Mn2O3? If this is 6- charge, that means the plus charges have to come from the manganese, and there's 2 of them. So what's the charge state of the manganese ion? 3+. So we're going from 4+ to 3+. It's being reduced. Now we've got 2 moles of it, all right? So we have 2 electrons being transferred here, right? But we're only going from a 4+ to a 3+, but that's okay because we've got 2 moles of it. So that's where the 2 electrons are coming from, or going to in this case. All right, the zinc oxide, now that one's going to be oxidized. So we write that one in reverse. That's going to be zinc solid plus 2 OH minus aqueous goes to zinc oxide solid plus H2O liquid plus 2 electrons. And that, now because we reversed it, I'm going to reverse the sign on E0 because now it's no longer a reduction potential, but I'm going to reverse it. So that's plus 1.249 volts. And now I'm just going to add them up because that's what's going to give us the voltage potential, whatever that is. My notes say it's plus 1.40 volts. Now you could have also gotten that by just plugging it into our equation, okay? The E naught of the cell is equal to the reduction potential that's happening at the cathode, and that's where reduction is occurring, right? That's going to be the reduction, that's going to be our plus 0.15 volts. And then we're going to subtract from that the reduction potential that's happening at the anode. That's an A. That's where oxidation is occurring. But in this case, I'm going to write down what the reduction potential is, E0, that's happening at the anode. But it's really the reverse of that. But that's okay. The negative sign in this equation takes care of that. So just make sure you don't reverse it twice. Okay? Just make sure you know what you're doing. And as I showed you many times, but I'll show you one more time, when you go back to the table and find these on the table, it's just the difference between, if I have to find these on the table now, where are they? And they may not be on here. Looks like one of them's here. Here, let's use purple. We've got this one here, and the other one was, are we so lucky that it's going to be here? Oh yeah, because we used it. It's the zinc one, this one, okay? That's just going to be the overall difference between those two. That's your 1.14. Or 40, sorry. That's the difference. That's the potential difference between those two reduction potentials. So any way you want to do it, right, you get what that answer is. You just have to understand how to use these equations. And then we can calculate, for 2 moles of electrons, we know how to calculate the energy that we get out of that, delta G naught, in this case, because it's under standard conditions, that's going to be E naught of the cell times the number of electrons times the Faraday constant, which gives us the charge on those electrons. But let's just take a closer look at this. I already explained this to you, so we don't need to spend a lot of time on this slide. This just gives you the information of where we get the Faraday constant from. This is our 9.65 times 10 to the 4th coulombs per mole. So this is our Faraday constant. But we've been using this already. I have explained it to you already. But now here it is laid out for you. This is the charge on one electron. This actually, you might have learned this in Gen Chem 1 when you looked at the experiments from, who was it? J.J. Thompson and also Millikan. I'm not going to go over those experiments again, but those are some of the old classic experiments that you learn in Gen Chem 1 about the discovery of things that they called electrons, and they were able to measure their mass to charge ratio. And Millikan was able to separate that out and actually determine what the charge of an electron was. So that's where this value comes from. This is just Avogadro's number. For 1 mole of electrons, this is the charge on 1 mole of electrons. That's all it is. But this number here, just an FYI, okay? The charge of an electron, that's what we call 1 minus. Right? For all of general chemistry, when we've been talking about what's the charge? 1 minus, 2 minus, 1 plus, 2 plus. It's really 1.6.02 times 10 to the minus 19th coulombs. Right? That's the one. It's much easier to just use 1, 2, 3 for our relative charges, but this is what the actual value is in the units of coulombs. So just a little FYI, that's where all that comes from. All right, so this equation here, the work in joules equals minus NF E naught of the cell. This is what we've been using. But this is all under standard conditions. So let's take a little delve into what happens when things are non-standard. Remember, under standard conditions are where we're at 1 bar, and we're at, I guess it's 25 degrees Celsius. And most importantly, everything's at 1 molar concentrations. So all the way back to those wet cells that we were working on, the electrochemical cells, where we have stuff in solution, that's all 1 molar. And the beauty of using things in 1 molar, and this will be a little bit of good review for you, when we're dealing with KEQ or Q or anything like that, mass action expressions, right? It's always the concentration of the products divided by the concentration of the reactants, raised to whatever stoichiometric coefficients, right? So I don't care, let's put a 2 here and a 3 there, whatever. But if you're at standard conditions, it doesn't matter what that mass action expression looks like, everything's a 1. So if everything's a 1, under standard conditions, your mass action expression will always have a value of 1. And that's why we use this as our standard, because it's really easy to work with. But now we're going to look at what happens when things aren't 1. All right? And to do that, we need to come up with something looks a little confusing, but it's not really. We're just going to take this quantity that we've been using all along, and we're going to substitute it into an equation that you're very familiar with back in, this was chapter 12. Delta G equals delta G naught plus RT times the natural log of Q. And Q is just the reaction quotient. So this is nothing new, hopefully, to you. Okay? And who remembers what happens at equilibrium? What happens to equilibrium, right? We've got, instead of Q, Q is equal to K, so I'll tell you that much, all right? But what happens to delta G? Not delta G naught. Delta G naught is always delta G naught. That's a standard value when everything's at 1 molar. But what happens to delta G at equilibrium? It's 0, all right? When you're at equilibrium, delta G is at 0 because you can't get any work done at equilibrium, right? Remember that's our little graph here where we have delta G over here, and we have reactants and products, and we have KEQ at the bottom, right? You can't get any work done at equilibrium. So when that happens, delta G naught is equal to negative RT times the natural log of Q. All right, that's just a little reminder. But now let's take this value now, minus NF E naught of the cell, or just E, because now it's going to be either standard or non-standard, and let's just plug that value in to delta G. Let's just substitute it in. And that's all that happened to get to this line here. All we're doing is substituting NFE into delta G. And then I'm just going to divide everything by negative NF. And that gives us this line. E of the cell is equal to E naught of the cell minus RT log Q divided by NF. And I'm just going to rewrite this a little bit to emphasize something that I want to show you in the next example here. Minus RT divided by NF. And I'm just going to put this log Q off to the side because everything else here is constant. I mean, R is always constant. Now in this case, this is the gas law, the gas constant, but we need the version that's in joules because this is all measured in joules here. So this is our 8.314 joules per mole Kelvin. And T is the temperature in Kelvin. N, of course, is the number of moles of electrons. And we know how to get that now. We've practiced that. How many moles of electrons are transferred in a reaction? And then, of course, F is our Faraday constant. So this term, once you're working with the reaction, that term stays the same. The only thing that changes is the concentration of products and reactants. And it's a natural log. So we saw this earlier when we were doing acid-base with buffers, right? And there was a log term in buffers. And it helped us mathematically to understand why a buffer works. You add a little bit of acid or a little bit of base, but it doesn't change the overall pH that much because it's a log function. The same thing's happening here, all right? This, by the way, is the Nernst equation. And it helps us to understand how the voltage potential changes under non-standard conditions. So how the voltage potential, I mean, that's what E of the cell is, right? Changes under non-standard conditions. So to show this to you, because it's really interesting. We're going to go back to that Danielle cell that we've kept using, the zinc and copper reaction, right, in an electrochemical cell. Let's take a closer look at that. All right, here it is again. All right, this is nothing new. This is stuff that we did a couple lectures ago. And we calculated what the standard voltage potential is for this electrochemical cell under standard conditions, right? So this is E naught of the cell. That's when everything's at 1 molar. And that's really all we've been using this entire chapter. And frankly, this is all you'll be doing in lab today as well. You're not looking at non-standard conditions. Right? But you've all used batteries before. Right? This is like a battery. Right? But I just wanted this example because we've used it so much already. And let's take a look at what happens to the voltage potential as this reaction commences. And here's the anode on the left in this case, in this diagram. Right? Zinc is being oxidized. So it's leaving the anode and going into solution. So the anode loses mass. Right? The cathode, the copper ions in solution are going on to the cathode, so the cathode gains mass as copper gets reduced. Which means that the concentration of ions in solution, and that's what's going to be our Q, by the way, ions in solution, the Q is going to change. We start with 1 molar on each. When we start with 1 molar on each, what's the log of 1 divided by 1? I don't care whether it's natural log or log to the base 10. What's the log of 1? Plug it into your calculator if you don't know. It's 0. All right, that's something you should always remember. The log of 1 is 0. So when we start this, here, I'll just put it up here. When we start this reaction, all right, let's just put this one here. E of the cell is equal to E naught of the cell minus RT NF natural log of Q. Okay? But if we start with 1 molar on each side, the log of Q is 0, which means this term goes away and the E of the cell is equal to our standard E of the cell, which we already calculated is whatever it was, it's on here somewhere. 1.104? Is that what it is? Did I calculate it? Here it is, 1.104. All right? So when we start this, under standard conditions, look, it even says 1 molar on our illustration, how convenient. All right? These two are equal to each other because this term goes away. That's the same thing that we saw in buffers, in pH, when you're at the pKa. When the reactants and products in your Q are the same, that log goes to 0, and the pH is equal to the pKa, if you remember that stuff. All right, so the same thing's going on there. So now let me go back, let me erase this, and let's go back here. Where are we? Come on. Here we go. All right, so let's just have some fun with this. So let's write this in. So E of the cell is equal to E naught of the cell minus RT NF natural log of Q. Now, at standard conditions, that's where we're starting. I need to get I need these notes here. All right, under standard conditions, where everything's at 1 molar, what are we going to have? We're going to have RT, well, that's going to be actually, wait a minute. It's 1.104 volts, right? That's what E naught of the cell is. Minus R is 8.314. T at 25 degrees, so that's 298 Kelvin. N, how many electrons are transferred here? Two electrons, so we've got a 2 here. And the Faraday constant, for every mole, we have 9.65 times 10 to the 4th coulombs. And that's going to be times the natural log of 1 molar over 1 molar. which we already know is 0. But we're going to keep using this value. This value is never going to change in my example. So let's just go ahead and calculate what that is right now. Let's call this 0.013. Okay? Now, of course, this is 0. So we know then that under standard conditions, E of the cell is equal to E naught of the cell, which is 1.104 volts. That's what we're starting with. Okay? And now we're going to let that reaction run, right? And the anode loses mass, the cathode gains mass, and in the process, the concentration of those solutions are changing. So let's look at what happens when 10% of the reaction has occurred. Okay? So at 10%, what are the concentrations now of the copper and the zinc in aqueous solution? That's all that matters. The solid concentrations of solids don't change. So Q is just going to be, let's put this up here. What is Q going to be equal to? The reaction goes as written. So the products, it's going to be the concentration of zinc ions divided by the concentration of the copper ions, right? So if 10% of this reaction commences, that means the zinc is going to increase by 10% and the copper is going to go down by 10% because we're going from reactants to products, right? Everyone with me here? So at 10%, we're going to now have E of the cell is equal to E naught of the cell, which is our 1.104, minus, and now it's going to be the 0.013, times the natural log of zinc over copper. And if the zinc increases by 10%, that's going to be 1.1 molar. And the copper went down by 10%, so that's going to be 0.9 molar. Okay? So I'm not going to plug it into my calculator. I've already done this. When you do that, you get 1.01, no, you don't. You get 1.101 volts. All right? Not much of a difference. And again, that's because the difference is going into that log function. And then we're just subtracting it from the standard. When we have 20% of the reaction that's transpired, all right, E of the cell is equal to 1.104 minus 0.013 times the natural log of, now what's the fraction going to be? 20% has gone from copper to zinc, so this is going to be 1.2 molar, and this is going to be 0.8 molar. Okay, see what I'm doing here? And when you calculate that, I got, this is 0.99. So it's going down every little bit. Now, I'm not going to take you through all of these steps, but I'll tell you that, yeah, I spent the time over this weekend to do all this, just for you, okay? So if we take this down, let me take you down to 90%, okay? And this actually, this is what happens. This is the sample exercise, if you look at this in the textbook. So this is sample exercise 17.5 in the textbook. When you have this cell and it's 90% depleted now, you would think our voltage potential will have gone away, right? 90%. I mean, it's practically gone. Well, let's take a look. E of the cell is equal to 1.104 minus 0.013 times the natural log of, now what's our fraction going to be? 90% is depleted. So what's the fraction? 1.9? Yeah, I was doing it backwards. Thank you for telling me. 1.9 over 0.1. And when you do that math, you still get a pretty large number. You might have noticed that, your dry cell batteries, when you put them in your remote control, to watch TV or in your PlayStation. Well, I guess PlayStations are charged with USBs, but anyway, you put the batteries in your flashlight or whatever, and I guess in a flashlight you see that the light kind of goes down and gets kind of weak. But in your remote control, it's like it's working, and then all of a sudden, it's gone. Okay? Even when it's 90% depleted, there's still a pretty good voltage potential there. Remember, that's just the potential, right? But you still have the 2 moles of electrons going through it. Okay? But the distance of the waterfall drop is getting lower and lower, but not that much. Even at 90%, you still have a lot there. So I went ahead and took it even further. I went to 99.9%, and I calculated it. Okay? I won't draw the whole thing out, but you can see what the fraction would look like. At 99.9% depleted, I still calculated a voltage potential of 1.035 volts. I even did 99.99 and 99.999 just to drive the point home here. I wanted to see how depleted did it need to be in order to get this just to drop below 1 volt for a voltage potential. And finally I got it. Okay? All right, but I went ahead and plotted these just so you can see really what's happening. And I would never encourage you to do your own hand-drawn graph like this. You need to use graph paper, right, with a good grid. But just to give you an idea of the trend, all right? Here's voltage potential on this axis, and here's the percent depleted. Okay, so 10%, 20, and down here 90, 99.9999, and all that stuff. And you can see for the most part, all right, you've got plenty of voltage potential there as it's being depleted. It's only at the very end when it drops off like this. All right, so most batteries will be very productive for you until they're almost completely depleted, and that's when it drops off precipitously like that. The textbook shows you that same curve in the context of your car battery. All right, it's the same curve. All right, cranking power of your battery. This is the chemistry of your car batteries. And if any of you have unfortunately experienced, you crank, and then all of a sudden, that's it, it's dead. All right, your car doesn't almost start. It either starts or it doesn't start. All right, and that's when your battery is depleted. And you can see that same drop off here. Now, these equations are very complicated, but it's the same principle that we've been doing the whole semester long. So let's take a little look at your car battery. Now, it already says on the slide what the reduction half reaction and the oxidation half reaction is. But let's just take a look at the overall equation here. Even if you look at the half reactions, can you tell what's being oxidized and what's being reduced here? Let's see if you can figure that out. What's being oxidized? Oh, by the way, there's a typo here. Oh, no, did I fix it? No, there's a typo. To balance this, there should be a 2 there. What's being oxidized? Can you tell? What would some of the strategies be to figure out? Oxidation states, okay, that's good. Let's look at oxidation states. And before we do that, look for the zeros. Look for the ones where it should be neutral, because those are easy to identify, right? Like, here's PB, here's lead solid. You know that's 0. So put a 0 in there. Are there any other zeros we can put in? No, that's the only one. But still, that'll help. All right, and then let's go ahead and look at the oxidation states. That's a great idea. So here's PbO2. Now remember, oxygen is always going to be 2 minus. So how many negative charges do we have in PbO2? 4. So what's the charge on lead here? 4 plus. Here we already know the hydrogen, we're given the oxidation state there because it's an ion in solution. This, it's a little tricky, all right? This is the hydrogen sulfate polyatomic ion. It's staying as a polyatomic ion. It's over here also in sulfuric acid. So the sulfur isn't going to change at all, because really the polyatomic ion isn't changing at all. Right? This is the same as HSO4. So what's left? Well, let's take a look at what's happening on the other side. Here's lead sulfate. Now you need to know what your polyatomic ions are. Okay? This is the sulfate polyatomic ion. It's 2- charge. So I just gave it away. What's the charge of lead in lead sulfate? It's 2+. Now that's going from 4+ to 2+. So here, we're not answering the question yet. The lead's being reduced here, right? But wait a minute. We also have lead 0. Look, we have lead in 2 states in the reactant side. All right? Here's lead 0. It's also going to lead 2+. There's your oxidation. So it's all lead, right? We have 2 forms of it. And one's being oxidized and one's being reduced. And they each have their own different reduction potentials. And here they are listed for you. So in the half reaction, okay, the reduction half reaction, right, here's your lead O2, right, your lead 4 oxide is being reduced. And here your lead solid is being oxidized, just like we deduced from the overall equation. So you can go ahead and calculate what the E0 of the cell is, right? Because here's the reduction potential for the reduction half reaction, and here's the reduction potential for the other reaction that will be reversed because it has a lower reduction potential, right? So that one's going to run in reverse. So then overall, E0 of the cell is going to be equal to the voltage, the reduction potential of the reaction that gets reduced minus the reduction potential of the reaction that's running in reverse. So that's 0.356, and that gives you a positive, a little more than 2 volts. And in your car batteries, if you've ever looked at them or read up about them, you've got about 6 of those cells all hooked up together in series, so you get about 12 volts of cranking power overall in your car batteries. But the drop-off is about the same. And you can run the same exercise if you wanted to, because here's the equation. RT divided by NF, that's always going to be the same for whatever this reaction is. By the way, how many moles of electrons are being transferred? In this case, 2. We didn't need to do anything to balance that. But if we had to balance it, you know how to do that, right? Just remember that when you balance the number of electrons to get how many moles of electrons are being transferred, that doesn't affect the voltage potential. That just affects the energy you can get when the flow goes over that voltage potential. All right, so anyway, you can run through all that and see. It's basically the same outcome that we saw before. You end up with a curve that looks like this in the end. So that's a little bit of insight into how all this affects you when you want to start your car in the morning.